Recording is rolling. It is Monday, August 15th. Right, so here's my plan for the next few days. I want to make sure that I cover a lot of the basics that we're going to be using for like the entire class. And let's start with some algebra. So we're going to be looking at like solving for x, solving in terms of variables we'll do a little bit with, some graph shapes, that sort of thing. Tomorrow I want to hit with you guys trigonometry vectors. You guys remember things like SOHCAHTOA, sine, cosine, Pythagorean theorem, that sort of stuff. Break out the protractors, do a little bit of science stuff on those. Okay. And then Wednesday, I want to cover a bunch of other science stuff like measurement, scientific method, SI system, measurement tools, dimensional analysis, that sort of thing. Okay. And then we'll see where we are by end of Wednesday. Okay. So let's start with some algebra equations. Now, I gave you guys this half page. I know it says algebra homework on it. This I'm not actually going to assign or pick up for homework, but I definitely do want to do some problems off this page. And if you feel really comfortable with this or anything else we do today, then that means you're in good shape and ready to move on to the next part. On the other hand, if you feel really rusty with things we do today, or you need lots of extra practice problems, then well, you have a whole page of practice problems right here. Right, so I'm going to start with, let's say, number, well, 3. I think number 3 is a pretty good starter problem. We got 8x minus 2 equals -9 plus 7x. Like that, okay? Okay, now, what's being implied here is you're supposed to solve for x, right? So there is some value that x could stand for, like some number that would make this statement true, where the left side is equal to the right side, right? Now, what could that be? Now, one way that you could go about this, and if you have some crazy equation, you might have to do something like guess and check. Right? Like, I'll plug in 1 for x. Well, that didn't work. I'll plug in 2 for x. Well, that didn't work. I'll plug in, or you can just like try a bunch of numbers, right, until you kind of hone in on the answer. But there's a process called algebra where you go through a series of steps and you can get to like x equals something pretty quick. Okay? That's one of the purposes of something like algebra, right? Solve for x, solve for some unknown. By the way, why is x the unknown? Right. So I feel like I've done a little bit of history here. Where does the word algebra come from? Like what language is that? Algebra. Anything that starts with al comes from where? It's like Arabic. Right. So the Arabs laid down the rules of algebra hundreds of years ago, and what they were solving for was what they called al-shayan, which was like the unknown thing, like the unknown quantity, al-shayan. Right. Well, eventually, Arabic culture gets into like European and Western culture through two entry points. One is like geographically the southeast of Europe, which is like through Greece. Right? And when this was all translated into Greek, the Greeks needed something to solve for. It's like, okay, well, it's not going to be Al Shayan and like the Arabic characters. So they went with the Greek letter chi, which looks like this. Right? There's Greek letter chi. Okay? And the other entry point of Arabic influence into Western culture was through Spain. Right? And of course, Spanish, they're using the Latin alphabet, just like we're using in English, right? Latin. Right? And oh, do you guys notice that? How many of you speak Spanish? You speak Spanish. Yeah. How about the sound sh, like that sh sound? Are there any Spanish words that have that sh sound, like sh? I can't think of any. So they're running into a similar problem that Greece run into. It's like, well, how do you translate this? Right? And like al shayan, like that sh sound, right? So hey, we've got this Greek letter chi, and the sort of Latin letter that's closest to that might be like x. And ever since then, x has been like the unknown thing to solve for, right, generically. All right, so let's go through an algebra process. And so we're solving for this x. Okay. Oh, now the algebra process says you're going to undo everything that's already there. I see 4 terms, so we're going to get like terms together, the x terms, and the others are constants, right? So I'm going to subtract the 7x over, right? So subtract 7x. Okay? Now, as long as whatever you do to one side, you do to the other side, everything's balanced, right? So 8x minus 7x is just plain 1x or x, and I still got the -2, that's -9, okay? And the other algebra step is to add this 2 over, plus 2, balance your equation. Okay, x is equal to -7. Okay, and that's it. Okay. Now, remember what that means. That means that this is the only value of x that you could plug back into the original equation, and it would give you a correct solution. Okay, so let's try it out. What is 8 times negative 7? Negative 56. Okay, minus 2 is negative 58. Okay, so I see that the left side of that equation is negative 58. How about the right side? So 7 by negative 7 is negative 59. Minus 9 is it's also negative 58. You guys see negative 58 equals negative 58? So it checks out. Okay. All right. Now here's where we're going to do some more off this page too, but I want to give you guys a different perspective, like a graphical perspective of how to solve this. Okay. Do you guys remember y equals mx plus b? Okay. Let's look at a graphing solution to this. Right now, you already know if x is negative 7, each of these left and right side is negative 58, right? And that's going to sort of translate to a coordinate. So what if I make this an equation and this an equation? Wouldn't it look like this? Y equals 8x minus 2, and y equals, I'm going to swap these a bit, 7x minus 9. Isn't that what this, y equals this and y equals this, like two different equations? That's okay? Okay. Oh, doesn't this take the form y equals mx plus b? Okay. So here's your slope, right? The rise over run. Okay. And here's like the y-intercept. Right? Okay. So let's put this down in graph form and see what this would look like and why it would also get you to the same answer. Put kind of the big quadrant 3 on this. That's kind of where the exciting part of this is happening. So I kind of know where we're going with the answer. Let's scale this. Let's see, negative 10, negative 20. It's kind of a weird graph, but it ends up working out. I got my x-axis, got my y-axis, 10, 20. And let's go 1, 2, 3, 4, 5, 6, 7, 6, 5. Like that. Okay. Now, if you forget how y equals mx plus b works, then you can always just create something from scratch and we backtrack even to that point. For example, if you think like if you're making a table of values, right? If you plug in 0 for x, then according to this top equation, what's y equal to? So 8 times 0 is 0, minus 2 is negative 2. So if x is 0, y is negative 2. That's about right there. Right there. And then what if x is 1? Let's see. That'd be 8 minus 2 is 6. So 1, 6. So over 1 up 6. Right there. What if x is 2? 16. 8 times 2 is 16. Minus 2 is 14. Over 2 up 14. Okay. See how these points are lined up a straight line? Okay. You can plug in anything for x, and you're going to get some different value for y, but they're all going to land, all the coordinates are going to land somewhere on that line. Okay, somewhere on that line. So let's set that up here. Okay, how about the second equation? Oh, wait, back up a little bit. Okay. So just to fill in the gaps here, you see the negative 2 is always going to be your y-intercept. So it's crossing at 0, negative 2. That's that point right there. 0, comma, negative 2. Okay. And then this 8 is the rise over run. So every step you take to the right, you go up 8. So from this point to this point, for example, it's over 1 up 8. Right? Rise over run of 8. Okay, how about the other one? 7x minus 9. Let's jump straight to the intercept and the slope and put it together that way. So you guys see the y-intercept's going to be negative 9. Plug in 0 for x, you get negative 9. So that's right there. Okay. And then the slope of this, it's pretty similar, but it's a little bit shallower than 8, so it's not quite as steep. Right? So I need a rise over run of 7. What's that going to look like? It's going to look about probably something kind of like that sort of, right? Where this has a rise over run of 7, 7 to 1. Okay. Now those lines are almost parallel, but not quite. Okay. And look where they cross. They cross right about here, which is at the coordinate. Didn't get it exactly, but it got pretty close. Negative 7, negative 58. I see they would kind of cross down there, which was exactly what we got with the process method, right? Negative 7 was the x coordinate. Negative 7 is the x coordinate where they cross. Okay, and then if you plug that into each of these, you get negative 58. Negative 58 equals negative 58. So it's like a y coordinate. Okay, so there's a graphical interpretation. Okay, guys right there. Okay, let's try something else. Kind of a curveball question, you guys. Number five. So 4m minus 4 equals 4m. This time we're solving for m, which be ready for that in physics because you're not always solving for x necessarily. We have all different variables you can be solving for in this class. Give you guys a head start here. Solve for m. Who can tell me what's m equal to? What's the answer to that question? Yeah. It is no solution. All right. Yeah, the teacher got it. No solution. All right, so let's try this both of those interpretations that we just did for the last question. Right. So if you go through that algebra process, let's say I'm solving for m. So maybe I want to, let's get all the m's on the right side. Maybe subtract this 4m over minus 4m. Do that to both sides to balance the equation. Goes away here. You get negative 4 equals, well, that goes away. 0. Oh boy. Oh boy. Okay, so two problems there. One is that what I'm solving for, the m, which is kind of like x, we're just calling it m, right? It's gone. Yeah, well, we're going to solve for. And the other thing is what I'm left with isn't even true. Negative 4 equals 0. Okay. So, yeah, so you're right. The correct interpretation that would be no solution, okay. Which is to say there's nothing you could ever plug into m and for m to the original equation to ever make that true. Okay. Now, what about like a graphical interpretation of that? How's the planet with the graphs? So x-axis, y-axis. Okay. What if the equations are like this? Y equals 4, well, instead, and maybe I'll say x. You guys get it? Same idea. 4x minus 4. And then this one could just be simply y equals 4x, right? Let's graph both of those. Y equals 4x. That goes through the origin. If x is 0, y is 0. 4 times 0 is 0. So that's that point. And then has a rise over run of 4. So that's a really steep rise over run of 4. Up 4 over 1. Every step to the right, you take 1. You go up 4 steps. And then what about the top? Because that's the bottom equation. What about this top equation? It's just the same thing, but we move down 4 ticks. Wouldn't that look like that? You guys see it? Okay. So the fact that those lines are what relative to each other? Parallel. They're parallel. They never cross. They never cross. There's no place where they're ever equal to each other. No solution. Okay. There's the graphical interpretation. Okay. All right, guys, ready to go a little harder? Let's go number, how about number 18? 18. Let's put it on negative 3 times 4x plus 3 plus 4 times 6x plus 1 is equal to 43. All right, I'm going to give you guys a head start. See if you guys can get me to the answer on number 18. If you know what you're doing, keep going. If you're stuck on the first step, what did you guys do for the very first step? How many guys were thinking distribution? Distribution, isn't that? All right, all right. So this negative 3 right here applies to two things inside parentheses. So I have to distribute it. Same idea with this 4. It applies to the 6x and also the plus 1, right? So I need to distribute. And so it's going to be negative 12x minus 9 plus 24x plus 4 is 43. Okay. Okay, so now I have this in an expanded state. I see 5 terms. 2 of them have the x, and 3 of them are constant. So we get like terms together. So these two guys tag together, that makes 12x. And then negative 9 and 4 makes negative 5. So I'll equal to 43. Add the 5 over. It's 12x is equal to 48. And then what's the very last step? How do you isolate x?
Divide.
Yep, divide by this coefficient, 12. All right, and that will bring you to x is 4.
I
yeah.
wanted to believe if you know that if you know your times tables, you can know that 12 times 4 equals 48. I've been doing these homework and yeah, I just memorized my times table. So
all right.
So if you're good enough at math, you can skip the process, but check your work to be sure.
Yeah, and you definitely want to know this process because, like, as we're going on throughout the year, we're gonna get like more complicated equations too. So yeah, you know your times tables. Yeah, good to know this algebra process. Okay. All right, you guys ready to go? Let's do this. Let's flip this page over. All right, so how about the other side here? Let's go number. How about number 29? That looks fun. Number 29. All right, so I definitely want to give you guys a head start with this one because there's one of two routes you could go with this. One that actually would be correct and get you to the answer, and the other that is just going to muddle everything up. Okay. You guys tell me, what's the first step you guys did? Move the 8 over. Exactly. That's exactly what you want to do. Okay. And instead of that, let me give you guys the counter example. Here's where things could have gone very badly. If you decided to square both sides first, here, and let me show you guys why you would not want to do that. In fact, I'll break out a new piece of paper just to show you guys. Okay, here's the wrong way. If you square both sides first, well, it looks like I have two things added together here, so it wouldn't have FOIL, F-O-I-L. Guys remember F-O-I-L? So it'd be this times itself, which would be negative 8 times negative 8 is positive 64. Then outside, inside, you'd have this times this, and then this times this for outside and inside. So that'd be minus 16 square root 5a minus 5. And then, yeah, plus, and then last, this times this, the square root would go away just for that last term, 5a minus 5. And then the other side, negative 3 squared is positive 9. Okay. So see, by starting out squaring, you have a square root before, you still have a square root. So that didn't really help anything. In fact, it actually just looks even more confusing, right? Okay. So yeah. Let's backtrack. Okay. Hopefully most of you guys did figure out, yeah, you do want to add the 8 over first, plus 8 plus 8. Okay. So it's gonna give you the square root is equal to 5, right? Now you can square both sides, right? So square the left side, square the right side. Right, square root goes away. Right, okay. You guys can definitely get this from here, right? Tag this 5 over. 5a equal to 30. Okay. And finally, divide by its coefficient 5. To 6. Okay. Guys get a 6? Not sure. Let's go back and check it. Take the 6, plug it back into the original statement. 5 times 6 is 30. 30 minus 5 is 25. Root of 25 is 5. Negative 8 plus 5. Oh, that's negative 3. Yeah, that checks out. All right, guys good? Guys ready to go trickier? Let's do this one. T squared plus 4t equals 21. Let's solve for t. You guys a head start. Solve for t. All right, who knows the answer? Who knows the answer? All right, go to Brian.
3.
3? Yeah, you guys like 3? Right. That'll work. 3 works. There's actually 2 solutions. Does anybody figure out? Yeah, what'd you get?
Is it -7?
And -7. All right, you guys got them. Yeah, +3 and -7. Okay. Now there's a couple ways you can get to the answer. You know what I should do? I'm going to split this paper in half and do it 2 different ways. Okay. Now, one thing you might notice is this is different than anything we've done before today. What you're solving for is being squared here. It's not being squared here, and there's also a constant, which means that this is going to fit what form? Starts with the cube. You guys are thinking quadratic? Quadratic? Okay. Now, however I solve it, I do want to get this all set equal to 0. I mean, there's 2 methods I'm going to go, but I guess there's a step before that, which is to get this all set to 0. So I'm going to go t squared plus 4t minus 21 is equal to 0, right? Okay. Now, here's where it branches, and you can do 1 of 2 different things. One thing you can do is factor it, especially if the numbers are nice, and this one does work. So it's kind of like FOIL, except it's backwards. It's really the reverse of FOIL. So I'm going to write FOIL, but whatever the answer is, if you go backwards through FOIL, it should bring it back up to the step. Okay. So let's do it this way. So if you factor it, okay. So it's going to be t plus something, or maybe minus. Okay. So what are 2 numbers that multiply to -21 but add to +4? What and what?
7, -3.
Yeah, 7 and -3. So I'm going to go +7 and -3, right? Okay, now here's really why I wrote FOIL, because I'm going to take that, I'm going to FOIL it to go back to the previous step, just to check my work. So first, outside, inside, last. Guys remember that? FOIL? Okay. So first, t times t, is your t squared. Outside, -3t, inside 7t. So 7t minus 3t, that gives you 4t. And then 7 times 3 is -21. Okay. So what's the advantage of this factored form? Well, now that you have things that are multiplied together, that gives you 0. If either piece is 0, the whole thing is 0. Okay. Okay, that's where from this piece you can get t could possibly be -7, and from this piece you could possibly get t is equal to +3. Okay. And they'll both work. So if you go back to the original statement, you can plug either of those into it, you'll get 21 for the one. Okay. Now, the other way you could go about it, especially if the numbers don't factor very nice, is quadratic formula. Is there a quadratic formula? Okay. So this says whenever you have this form, I'm going to throw x in here just to be really generic about it. I can switch sheet color. If you ever have ax squared plus bx plus c is equal to 0, which is the form that we have, right? Then this is already solved for you. X is always -b plus or minus the square root of b squared minus 4ac, all divided by 2a. How many of you guys have the quadratic formula memorized? There's quadratic formula. About half you guys? All right. That is a good one to be able to pull out of your back pocket. Remember when you might need that. Okay. Okay. So let's try it out. Now, instead of x, I have t. So I'm going to say t equals, okay, and then those pop in the parts. So -b, so let's say -4. Plus or minus, plus or minus, that's where I can get 2 answers. Okay. Square root, see, 4 squared minus 4 times, there's an applied 1 in front of this t squared, so 1 is a, and then c is -21. Now I've got 2 negatives here, so get careful about that. 2 negatives make a positive. And then all divided by 2 times 1. So t is equal to, let's clean up all this square root stuff. Guys, what's 21 times 4? 84, right? And then negative negative makes positive. Then 4 squared is 16. So isn't this 16 plus 84? And what's that? 100, right? What is the square root of 100? 10. So it's negative 4 plus minus 10, all divided by 2. Okay. So let's see, what's negative 4 minus 10? It's negative 14 divided by 2 is negative 7. Or negative 4 plus 10, that's what, 6? 6 divided by 2 is 3. Oh, hey, that's the same thing we got before, right? So 2 different approaches get you the same thing. All right. Here's the thing. Right. Now, say, how could you have 2 solutions? Hey, if you were to graph this, if you said y equals t squared plus 4t minus 21, what shape do you think that would look like on a graph? All right, start with the P. Parabola. And if that's set equal to 0, okay, I know exactly what that's going to look like. Some blank paper somewhere. There we go. -7, positive 3, t-axis, y-axis. It's going to be a parabola that looks like this. Right, that's where the equation set equal to 0. That's like the x-intercepts the graph. You guys get that?
Total skewed because of the multiplication power makes it kind of linear.
Yeah, you could. Yeah, but we did a word like a linearization last week. Yeah, with the circle where you like linearize the parabola. So yeah, you could possibly do something like that.
Yeah, the goes linearly, but the exponent goes exponentially.
Mm-hmm.
So overall, the exponent does a lot more than the 4 does, but
yeah,
it still has an influence on it.
Right. Yeah, the power will control the shape. Right. What type of curve is in them that right, that coefficient will just like stretch it. Right? Yeah. Right. It was wanted to tell you guys about this too. I did want to tie this to physics, right? Because what could this possibly represent? Why are we looking at this parabola thing? I want to give you guys an example. What if you had something like this? If you had it, what if you're up in a tree house? Right, here's the ground, and you took a ball, and you just chucked it straight down at some speed. Okay, it's going to crash land on the ground. Okay, I wonder, hey, I wonder how much time does it take to reach the ground? Something like that. Now, depending on like, here, what could affect how much time it takes to reach the ground? Do you guys think the height of the tree matters? Yeah, right. Closer you are to the ground, less time it'll take. Do you guys think how fast you throw it down matters? Yeah, faster you throw it, shorter time to reach the ground. Do you guys think the gravity field of the planet matters? Right. Now, all those factors matter, and the equation of it might look something like this. You guys are going to see some very similar looking equations here in the next couple of weeks, right? Except they'll have units attached to them, not just numbers, right? Right. So what this would mean is that it might take like 3 seconds to reach the ground. That could be one in solution, like positive 3 seconds. Right? Now, what would the negative mean? I can tell you the interpretation of that. So negative would mean if you're watching it hit the ground, let's say you filmed this whole thing, and then you ran the film in reverse, you watch it go back, go up, right? Except instead of somebody throwing it, it's like, well, what if there was like maybe, I don't know, maybe a side-by-side ball that was following it that had been thrown from ground level, like way back here, right? So here's the story back forward in time. Somebody throws up a ball here, okay? And then on its way down, right as it's passing the treehouse, somebody chucks the ball straight down so they travel side by side and bam, and reach the ground from the treehouse to the ground in 3 seconds, okay? Now, if you go backwards and then just follow the one that was thrown like way back here, you guys want to take a guess how many seconds it takes for the ball to go from here to the treehouse?
4.
How about 7 seconds, right? And in fact, it's negative means it's in the past, right? So from the treehouse back to it's like 7 seconds in the past, -7. Okay, you guys get that? Okay. Let's do. We have you guys solve in terms of variables. Solve in terms of variables. All right. Let me write that out. Solve in terms of variables. Okay. Now, what we're about to do here, my AP kids, I have to do all the time. my conceptual kids, hardly ever, and then for honors, yeah, maybe here and there, you guys might see some of this process what we're about to do. Okay? We're going to come up with some general solution. Okay? In fact, I'll give you guys an exact physics example that you guys are definitely going to see this year. Can you solve for that V in terms of everything else? Go ahead. Gonna give you guys time. Solve for V. All right, who figured it out? Yeah, what you got?
Should it be V equals 2GH? Well, V squared equals 2GH.
Okay, so V squared equals 2GH, and then so you're one step away. Then the last step would be
would it be to do it V equals the square root of 2GH?
That's it. That's it. Yeah, it's correct. 2GH. All right. So let's go through this. Maybe no, this is it's the same process we'll be doing all day today, right? Except it just has some letters in it. Right? So I'm going to multiply both sides by 2. So times 2 times 2. That looks like mv squared equals 2mgh. Hey, how about divide both sides by this coefficient m? Divide by m, do it to both sides to balance the equation. And then last step is square root. So v is square root 2gh, just like that. Now, what's the tie into physics? Right. What if you guys can figure out what these variables stand for? What do you guys think the h stands for?
Height.
Like a height change, right? Height change. What do you guys think the g stands for? Gravity field. Yeah, like different planets might pull with different gravity fields, okay, which is a type of acceleration. Tell you guys real fast, acceleration is like a rate change of velocity. We'll go over all this stuff like next week especially, right? But can you guys see a speedometer reading in your car? Went like 30 miles an hour. And then you slam on the gas pedal, it goes, starts moving up. What if you really slam on the gas pedal? It goes like, wouldn't those be like different accelerations, like different rates that you're changing your velocity? And you think gravity pulling down on a planet causes you to speed up faster? What do you guys think the V stands for that you just saw it for? Maybe the velocity you pick up to, how fast you're going, like a speed. Okay. What do you guys think the M stands for?
Mass.
Mass. You notice that it canceled out. So let's go back to this tree house. And I'm going to tell you a very similar story. I'm just going to end this a little bit. Instead of chucking the ball down, what if you just dropped the ball? So we're going back to this tree house. And I'm just going to drop the ball. And I wonder when this ball is landing, what's its velocity, like its speed, like how fast is it crash landing into the ground? Okay. Well, it has something to do with this height change, h. It has something to do with the gravity field that you're in, g. And the ball has some mass, but according to what you just solved, and later on this year, you guys will see why this is the case. Here, does the mass of the ball have anything to do with how fast it's going? Not according to this. So if I change the height of the treehouse, if I change the gravity field, like what planet you're on, those would, right? But what if I had a tennis ball and I dropped it, and I go back and I drop a bowling ball? Would a tennis ball and a bowling ball fall side by side all the way down?
Yep.
Yeah. In fact, this is a very famous experiment going back to 1589. This is what you guys know the Leaning Tower at Pisa over in Italy, right? Galileo went to the top of that tower and did exactly that experiment. Dropped different stuff. It all fell together, freaked everybody out. It's sort of the beginning of modern science right there, that experiment. Okay. But now look what you have. You have a generic way to find the speed of anything that's falling, regardless of what planet you're on and regardless of the height of the treehouse. Yeah, look at that. How about we have to do some basic graphs? Okay. Any questions so far? That's right. Right, let's look at some graphs. So there are, of course, all kinds of graphs in the world, but there's really only a small handful of graphs that you guys are going to regularly see throughout this year. Okay. So let's look at these graphs. Okay. Yeah, I'm gonna do 7 graphs with you guys. Let's do 7 graphs. All right, get my XY axes going. This last one, I'm actually gonna make like a sideways T shape. Forget to do that. Okay. Sorry. Okay, so x-axis and y-axis. Okay. Now, x and y is a very generic way to label these axes. But in physics, they could be any variable or sometimes any combination of variables. And you guys might even remember this just from last week. I had you guys measure a bunch of circles, areas, circumference, radius, right? And you guys graphed circumference versus radius. You got a linear graph. You guys did area versus radius, got a parabola. And then you did area versus radius squared, and it can turn out linear again. You guys remember that? Okay, so what are some basic graph shapes you guys want to see with lots of labs that you do in this class? Okay. Well, one possibility might be something like this. Maybe you treat x as your independent variable, and you plug in lots of different x values. Maybe it's like the mass of a car, for example. Hey, how about the mass of something you drop from a treehouse? Okay. And then you see like, how fast is it going to be? This might be a v versus mass graph for dropping things from a treehouse. And I can tell you what that graph is going to look like. It's going to look something kind of like this, where regardless of the your input mass, or like the x variable in this case, the y variable stays the same. Like the speed of the object is about the impression of the graph. Okay. So if you ever see a graph like that, what does that tell you about the relationship between the two variables, x and y? How about that there is no relationship? You can make x whatever you want, and y is like, I don't care. I'm just going to be whatever I am, right? So this is called no relationship. Okay. No relationship between the two variables. Would that also be true if you get a graph looks kind of like this? Maybe you're changing y all over the place, and x is just saying, I don't care what y is. I'm just going to be whatever I am. Okay. Would that also be no relationship? Yeah. Okay. For the two variables that just don't care about each other. Okay. Again, a really good example is this right here. Variable cancels out. Okay. If you put that variable on one of these axes, your graph looks like one of those. What if you double x and y also doubles, and then you triple x and y also triples, and then you do 10 times x and y is also 10 times? What is that graph called?
Linear relationship.
Linear, yeah. I'll say linear or direct. Now, if it's direct, usually that implies that it goes through the origin, like I drew on this graph, but might not. All right, so this could have some slope. I'll call the slope m just to steal from algebra. Okay. Could that be like y equals mx plus b? Is okay? Y equals mx plus b for a line like that, right? And if it does go through the origin, then what is your b equal to? It would just be 0. So it'd be just plain y equals mx, right? So like whatever your x is, if you multiply by some scaling factor, all your points are going to line up in a straight line like that, right? Actually making these graphs a little too perfect. Like in your lab data, you might remember this from last week. You might get like a little bit of below, a little bit above, you know, won't necessarily land exactly on the line, but should be pretty close, right? We're all trying. What if you do this? What if you start off with a small x value and get a huge y value, and then the bigger you make x, y gets smaller and smaller. So the curve of best fit would be something kind of like this. What's that relationship called? It starts with an I. You guys think an inverse relationship? Okay. This would be like y is proportional to 1 over x. Okay. That proportion, think of it kind of like an equal sign, like what? In fact, it might be that. It might just be y equals 1 over x. Okay. But there might be more to the equation. Maybe it's some constant divided by x, or right? It might even be 1 over x squared. Could make a very similar looking graph. What if you increase your x values, but y increases at a faster rate? Like if you double x and y quadruples, and then you triple x and y is like 9 times. Okay? And then you get something that kind of curves up like this. Okay. What shape do you think that would be? How many of you guys think that probably looks like a parabola? You think a parabola? Okay. So the more general term would be a power relationship. Okay. I'll say, for example, parabola. There are going to be a bunch of parabolic relationships in this class. Parabola. You guys saw one last week, right? Area versus radius of a circle. Right. Oh, yeah. Oh, right. Um, so this might be, for example, y is proportional to x squared, right? Even y equals x cubed or y is equal to x to the fourth would create really similar looking type curves. But most often in this class, it's like y is equal to x squared or y is proportional to x squared. Okay? I'm saying proportional to because I might be leaving off part of the equation. Okay? How about this? What if you make x bigger and bigger and y increases but at a slower and slower rate? Right? That's maybe not even approaching an asymptote. It's just not increasing as fast. Right? Maybe even at first glance, it almost looks like linear with a huge y-intercept. And you think about it a little bit. Hold on a minute. Wouldn't really make it sense for if x is 0 for y to be a huge number. Maybe 0, 0 makes more sense as a point. Go back to the lab, get data that would confirm that. Okay? And so it kind of hooks down like that. What do you guys think that relationship is? I guess
limit relationship. That'd be.
Do you guys know what a square root looks like? That could be a square root, right? Right. So this I'll call it root. For example, y is proportional to x to the 1/2 power, or y is proportional to the square root of x. Okay. Well, I was going to ask you guys, but what is a 1/2 power? For example, what is 9 to the power of 1/2? That's 3. What is 49 to the power of 1/2? That's 7. We do one more. What is 64 to the power of 1/2? That's 8. What do you guys think the 1/2 power means if you didn't know before? It's like a square root, isn't it? It's like the same thing. Okay. I bet a lot of you guys knew that already, though. Okay. So 1/2 power square root, same thing. So actually, you know what? This graph is kind of like this graph in a way. It's just still a power relationship. It's just like a fraction power. Okay. And how about this? Actually, those 6 right there is should cover most of them. And then maybe December or January, you might possibly see a graph that looks some version of this. And what is this graph called? You guys know like sine and cosine curves? It's kind of what that looks like, right? Okay. So I'll call it sinusoidal if it like oscillates back and forth, oscillates. Okay. So this might be some version of y is proportional to sine of x, or even y is proportional to cosine of x. Okay. Now sine and cosine have the exact same shape, just one is shifted from there. So you could take a y equals sine x, y equals cosine x, and just shift them, and they would overlay on top of each other exactly. Okay. All right. You guys okay so far? All right. All right. Let me throw a couple of challenge problems you guys here at the end. Okay, let's do solve in terms of variables. Suppose you had something like this. This is one you're going to have to solve for a lab in a couple months from now. Can you solve for A in terms of those other variables? Solve for A. Walk you guys through this. Maybe multiply both sides by 2. Divide both sides by t squared. You get something like that? Okay. Where could you see something like this? A few weeks from now, you guys are going to do an Atwood lab. You're going to have a pulley, a couple of weights. What do you have? A big old weight here, a little tiny lab weight here. Oh, here's a whole box of lab weights, right? I see these? Okay. And they're connected by a string over this pulley. Okay. Do you think it wants to move like this? Do you think it's going to speed up as it's right? Do you think the rate that it speeds up is called A acceleration? I guess a little bit about that, like speedometer needle moving at some rate. Do you think X? What do you guys think X represents? Maybe the position change. Like if they go like 1 meter, for example. What do you guys think the T stands for? If you time this with a stopwatch, right? So how much time does it take to move some distance? Plug it all in, you can get the rate that it's speeding up. Right, guys can see this. We'll make sense of this equation probably next week. I'm looking at. Okay. How about? Okay, I'll walk you guys through this last one. How about time period of a pendulum equals 2 pi times the square root of L over G. This will be a lab that have you guys figure this out yourselves. Something, right? Hey, if you have a pendulum that was some length, you guys think L length could be length of a pendulum? You put all the mass in the bottom on the end, okay? And you calculate how much time it takes to swing back and forth. Do you think you could determine the gravity field of the planet that you're on? Okay, let's try it out. Some algebra. Divide both sides by 2 pi. Square both sides. Cross multiply. And finally, divide both sides by the time period. Boom. Now you have a general formula to figure out the gravity field on any planet just by swinging a pendulum back and forth. Boom, there it is. That's it. And so algebra is a really powerful tool that you solve all kinds of stuff. That's in terms of variables. So, all right. We got that. Yeah, you guys have a great day. I'll see you tomorrow for some trigonometry.